I will just give a bit introduction around Oraclize because I guess that most of you already know what it is. And then I will try to show you some of the latest things we have released that provide like on-chain verifiable authenticity proofs, and some of the work that we would like to be doing with Swarm. So we are looking for feedback, of course, and to see if there are other ideas. So first of all, well, it will be offending for most of you to introduce the problem in this way, but we all know that the EVM cannot reach out to the internet for technical reasons, and because basically it's impossible in a decentralized way to find consensus on whatever a given, even maybe non-deterministic centralized data source is providing. So the problem basically is that there are so many different projects that are trying to build smart contracts on Ethereum and on other platforms that need somehow to receive data from the external world, and there are so few data sources that are pushing data there that 2 years and a half ago we started seeing that problem coming, and we started to design a very generic system, a very general purpose system, which is Oraclize itself, to try to overcome this limitation and connect pretty much any data source, so any provider of data you find on the internet, or maybe even Swarm itself, IPFS, or data source in a very general sense, with different blockchains like Ethereum itself, but also Bitcoin and others. So the idea is to try staying as agnostic as possible while providing strong security guarantees. So what does it mean? It means that, you know, if I don't know, Poloniex wants to send a price feed to the blockchain, of course it's trivial for them because they just have to sign their own data with a key which belongs to them, and they send the transaction, and it's very easy to verify. You just check the sender of the transaction and that's it, right? But of course, this is not something that, well, Poloniex is not doing it, and we believe that most data sources will not do it. Because on one side it's not really scalable to just keep sending data on-chain continuously, and on the other because we believe that most data sources shouldn't interact with the blockchain and care about the different chains around the Ethereum mainnet, the testnets, or this or that context. I mean, they are already providing data via web APIs, and there is no reason to believe they will start to expose data directly on-chain. Also, today, many applications just cannot leverage data because those data sources are not sending their data today. So using Oraclize, you can have like a good guarantee of the authenticity of data with pretty much any data sources without waiting for them to adapt or to integrate or whatever. So the idea is that there is this, well, it's a company basically, so we have 10 people at the moment, 9, based in London, and we provide this as a service. So this is a centralized system, which is quite ironic, because of course the blockchain is about getting rid of, you know, unnecessary trust lines and centralization points. And here we are trying to provide a centralized service in a decentralized context. So this is quite ironic, but we've seen a bit why we believe that this makes a lot of sense. So basically, the Oraclize solution consists of, you know, sending on-demand data to a blockchain smart contract, and this data, which we call trivially a result, can be referenced in the query, specifying a data source. The data source is like the context. So a context might be IPFS, it might be Swarm, might be an HTTP API or something. It might be, I don't know, even Berthani itself. It can be anything, basically. And then a description of the query. So the description means something that describes in a unique way which kind of data you want. Then Oraclize will process this query and we send the result back. But along with the result, we want to send some kind of proof showing that, you know, Oraclize didn't tamper with the data. Because of course we are a centralized party, so why would you even trust us? I mean, it doesn't make any sense, right? And you shouldn't. So this is why we provide this kind of authenticity proofs. We'll come in a bit to what authenticity proofs are and which kind of guarantees they give. But the idea is to to have the Oraclize engine in between, which is basically a distributed network of machines that we manage that contain many trusted computing devices and many attestation techniques that I will explain later. And this Oraclize engine is providing a connection between like different blockchains and any data source you can possibly imagine, I would say. So there are different ways to interact with this piece, with the Oraclize engine. One is trivially an HTTP API, so you can go straight to the HTTP APIs of Oraclize and say, could you please get the data from Wolfram Alpha asking what's the temperature in Berlin, and provide an authenticity proof, so that they can prove in court that at that point in time, Wolfram Alpha has really, provided that piece of data and not something else. So you might say, well, if they provide a signature, that's all I need. Yeah, that's right. But most data sources don't provide signatures on their data, and there are not really, there are different ways you could provide standard signatures, but there are so many different standards that those APIs are mostly not using any. Very complicated because most of the guarantees you typically need are already provided by TLS. So when you have a secure channel between like the client and the server, that's you know the connection is safe, the data is authentic, but basically you cannot prove it to a third party. So this is the problem. So the trust model that we're using is based on three main categories, three main techniques. So the first one is the easiest, like the data source is signing the data. So if the data source is signing the data, Oraclize is just a carrier, basically saying, okay, so that data source, for example, CryptoCompare, which is the API that is being used, I think, even by Mist, to get the average price of Ether and blah blah. So CryptoCompare is using this standard proposal to sign data. It's basically just an extra field in the HTTP header. And if you use Oraclize, you specify that the data source is providing a native proof, so a signature, and Oraclize will send the actual result along with the signature. So in that case, the only thing that Oraclize does is really connecting the data from the data sources to the different blockchains. So you might even skip it and just do it yourself, but it's just convenient to use it because there is a nice framework which provides solidity APIs and blah blah, and it's very easy to verify transparently what's going on, basically. But in the case when the authenticity proof, the signature is not provided, it's more complicated because we need to prove to the smart contract possibly, but in general to third parties, that the data that the carrier has fetched from a given data source is really authentic, right? So the way we do it traditionally is TLS notaries. So this is how we started 2 years ago, providing these kind of guarantees. And unfortunately, most people believe that this is the only guarantee we give. So we have seen some papers mentioning our work. They just say, yeah, Oraclize is broken because it's based on TLS notary, and that's it. And TLS notary is broken. Okay. Well, Oraclize is not based on TLS notary only, so it's very agnostic to the type of authenticity proof. And we are already integrated with many other techniques that I will be talking about in a bit. But in general, it's true to say that TLS notary is the one being most widely used at the moment. So TLS notary is a nice protocol, which unfortunately doesn't work anymore after TLS 1.1. So from 1.2 on, it will just not work. So at the moment, that's not really a problem, but in a few years' time, TLS notary will simply not provide security guarantees because it's not compatible for the way it works. Well, there is a nice trick. I will not go into details unless somebody will ask questions afterwards. But basically, there is just a nice splitting of the TLS client secret during the handshaking phase. And one part of the secret is kept by a provably fully locked down instance, which runs somewhere. And the other one is kept by an untrusted system, which is Oraclize itself. So if you can prove that the party with the second part of the client secret is a piece of code being executed in a very specific way, then you can prove that your channel is safe, basically. And since that party is basically a machine running on an Amazon Web Service Cloud instance, if you can get somehow a proof from Amazon itself that that machine is safe and is executing that piece of code with no possibility of alteration from third parties, then you're proving that, according to Amazon, the context is safe, right? The communication channel is safe. And this is all TLS Notary and specifically PageSigner in that case do. So basically, they provide some signatures, a collection of signatures and a collection of information that you can use independently at any point in time to verify that that connection, that TLS connection was really safe, and so that that piece of data was really coming from the data source. Even if the data source was not providing any kind of signature. Of course, this means that we are trusting Amazon, right? So why don't we go straight to Amazon saying, hey, could you please just sign the data coming from the external data sources? Well, the idea is that you shouldn't trust a single party, of course. It's much easier to trust Amazon than Oraclize, basically because they have much more than us at stake. They have a reputation at stake, but still it's not enough, right? So this is why Oraclize is being agnostic also to the technology, and let's see if it works now. Yep. So basically, we are trying to stay agnostic to the technology. Yep, please.
So you're kind of saying, if you had a way to verify the state, which is the trusted computing thing, right? Irrespective of Amazon or whoever else, you could still get the state.
Yeah.
And in fact, the trusted computing stack actually has a TLS equivalent, which actually does it for you. Then why?
Yeah, that's correct. So basically, the why, well, this is if you have a trusted computing device, the trusted computing device by itself is not doing much, because it's just saying that according to the provider of the technology, the technology is safe, and you believe that this is true because the machine is in front of you.
This is a state and
is in front of you.
This is a previous state, this is a state that has changed, and you could provide the hash of all these things, and that's what it does.
Yeah, that's correct. But even with trusted computing, if you don't have an attestation technique, you will never be able to prove it to a third party, right? So if you prove it to a third party, the proof is just a claim coming from the producer of the technology, saying, according to myself, that execution was safe on that device, to my best knowledge. And that's all it does. So even with technologies like Intel SGX or many others that you see mentioned here, all you get to the external world is just a proof, a signature coming from this attestation, saying, okay, according to Intel, according to Samsung,
It's not technically according to Intel. It's according to the platform that runs it. If it's like the DAA, your attestation key is the thing that actually gives you what it is, and say that's the claim you make. You're trying to transpose the trust across. You don't have to. So, for example, in DAA, you don't have to have the trust of the provider per se. That's the proof.
Yes and no, in the sense that the chain of trust goes up to Intel anyway, because the key is issued by Intel, and if Intel doesn't issue for you a production key, then you cannot generate any proof, and you can just stay in debug mode, which means you can read the memory and all the security model is gone. So basically, all the chain of trust goes up to Intel anyway, even because you are trusting the producer anyway, since the device, the hardware is owned by them. You don't know if there is a vector, you don't know. There is always a trust line open with whoever designed the technology and whoever delivered to you the chip. Maybe it's not even Intel, but it's the carrier or the NSA or whatever, right? So there is always a trust line open, even if a given technology on paper looks super safe. Intel SGX is super cool on paper. We have been using it for over one year now. But the problem is that it's still very new. it's still being challenged a lot. And
I think there were some attacks probably.
there are some very recent attacks, and this is the reason why we are not using it in production. So we are using it internally to give guarantees to ourselves, but not to give it to external.
You could actually have your own if you are that keen. It's not hard to just create. So I wrote a paper 10 years back, more than 10 years back now, kind of proposing this kind of version of model where you would have. All you need to do is just build one yourself. If you trust yourself and everybody trusts you.
Yeah, but if you have trust in yourself, you can just sign the data.
No, it's everybody else doing that, right? And everybody trusting what you're doing is true. That's the second part of the story.
Yeah, right. It depends if the data you claim can be verified by third party or not, which in most of these cases it's not possible.
Yeah.
So we'll come to this in a bit, but typically because it's not deterministic, because the API is not public, because whatever. There are many different reasons. So the idea behind Oraclize is that we want to provide as a service a way which can leverage these techniques with more than one technology provider, more than one kind of proofs to secure the process, so a process in general. So in that case, it was designed for the Oracle service on Ethereum, but we're already using this even in other contexts which have nothing to do with blockchain.
You could also do Quorum, right?
You
could do Quorum. So like, easily, and then you can have like many of them, and then if all of them.
That's correct. So that's the very idea. The idea is to say you don't want to trust a single technology, but if you get a proof from each one of these techniques, each one of these technology, even if one is broken, doesn't really matter. Well, if the proofs are valid and the result is wrong, it means that at the same time all these technologies were broken and there was a malicious attacker which got access to the physical machine, which is quite unlikely. It's still possible, but it's it's a good guarantee. So the way how does it work in practice? So let me show you. This is something some of you might have already seen. So this is a client-side tool which is based on a library we released, which is called Proof Verification Tool. The Proof Verification Tool is just a single tool that you can use to verify all these different proofs we provide. And basically this is just a client-side tool based on it. You can download it and execute it independently, but for convenience it's also on our website. And it just connects on the client side to, like, here it's an Infura mainnet, ATH node. And all it does is it downloads on the client side, 12 hours of logs, so that's why it's so slow. And it will check for the transactions that Oraclize has sent so far, and we check the proofs, each one of them off-chain. And we try to see if we have ever sent anything malicious. So the proof most of the time is sent over IPFS. So sending it over Swarm will be an alternative. So the reason why we send it over IPFS is that not all the proofs are verifiable on chain. So those that are not verifiable on chain, so they can't be verified in Solidity, to make things clear. Most of the times we just send the IPFS multi-hash of the data, and we guarantee the persistence of the data via the IPFS persistence consortium that I will show you in a bit. This is all something that will be nice to replace with Swarm because basically it provides stronger guarantees than the persistence consortium on IPFS. Also because the persistence consortium, to my knowledge, is not used by anybody other than us. But as you can see here, there are different types of proofs, but most of them are TLS Notary. This is the mainnet at the moment. On the testnets, there is much more diversity, so TLS Notary is not the one being used that much. But the point is that once you write a smart contract, if the code was not written in a way that you can change it and disapprove, then it stays like this, of course. So many contracts have been running for a long time, and this is why they all have TLS Notary, because the others were integrated during the last year. As you can see here, there are two ledger proofs that I will show you in a bit. But the idea is that you download them on the client side, given the on-chain multi-hash, IPFS multi-hash reference, and you check it with this proofs. So that's it. So we use different technologies. This is already something I said. You can use it to access APIs, IPFS, Swarm, other things like the random data source we just released and the computation data source. So there are two special data sources. One is the computation data source indeed, which is yet another way to execute off-chain in an auditable context some piece of code. So we didn't push that much for that specific thing on the community side of things. We have been using it quite a lot with enterprises. And this is something that has been working for over one year now. It's not super exciting compared to many other techniques that other people are building, because it doesn't really provide, again, cryptographic guarantees. But it's very general and provides, again, a claim backed by one of the attestors. So what does it mean? It means
essentially what you're doing is you're layering, and you actually have different layers.
Yeah, that's correct. That's correct.
And what you could do is you could actually do the same thing you were proposing previously. You can have multiple layers, and you can actually have different layers doing different things, and then you could actually do averages. So
that's what we are doing, but it's not us that should do the average of whatever aggregation.
Okay.
Otherwise, it will be applicable.
Okay.
So it should be that civic one.
Okay.
So we are trying to build all these pieces that anybody can use to do it independently.
Yeah.
So the idea is, for example, with the computational data source, is that you can, well, I don't have slides here unfortunately, but I can show you later if you're interested. So the idea is that you can define a piece of code that will run in a given fully locked down Amazon context again, and you can verify by yourself that according to the Amazon signature, that code was the one being executed, the result is coming from that code, and the machine was fully locked down and not accessible by anybody. So for example, the machine is based on a public snapshot, and with a given ID, which Amazon promised not to change. So this is all backed by Amazon without them even knowing, basically, because we are using some techniques that are already out there, right? They were not designed for this specific use case, but they can be used in this way. So the idea is that every time you want to execute a piece of code, for example, we are using it for checking an on-chain, an RSA signature, because until Metropolis we cannot do it on-chain, but we needed it for a project. And we just have a temporary throwaway Amazon machine that does it, and it's fully covered. Another thing is the random data source, which is basically, well, I'll show you later. Examples, let's skip. This is the boring part. You can all imagine what can be useful. So yeah, this is mostly it. I just want to show you a couple of things, maybe in Solidity. We have an integration with Bitcoin, but yeah, let's skip it for now. This is quite interesting, but yeah. So the random data source was released 2 weeks ago, and there is a white paper we released of it. Well, it's not really a white paper, let's stop calling it this, it's just a PDF. Which contains, I mean, we are not academics, so we will not call it white paper, it's just a PDF containing 20 pages of explanation around the idea behind the random data source. And basically, the idea is to try to circumvent some kind of attacks, like reply attacks and others, via trusted execution environments. And what we did here with the first one that is already working and being used is using the Ledger NanoS with a custom applications running there. And basically they have a secure element chip and an attestation, so the Ledger is providing a signature on the fact that the execution is safe and the random number is coming from there. And the nice part is that it's verifiable on chain Solidity, and it's not even costing that much. I mean, with like, I think 40,000 gas, you can verify the whole chain. You can verify the whole thing for random number. Chain proof verification for the native proofs, following the HTTPS header signature standard I mentioned before. So this is doable on chain as well. And that's mostly it. I will show you, if I still have a couple of minutes. Well, the IPFS Persistent Consortium is a project that Python Merriam released, when was that? I think over 1 year ago. January 2016. And basically this is just, it's very simple, it's just a Python script that you promise to execute, in which different IPFS nodes can have a manifest claiming which kind of multi-hashes they want to maintain, to keep stored. So it's a promise saying these are the files I'm pinning, basically. And everybody who has this script can check the manifests of other nodes they have whitelisted and keep a copy themselves. So it's just an agreement between different nodes to keep a permanent copy of a given file. And of course, you don't need to trust them, right? But you need to be 100% sure that somebody will have a copy. So if you don't want to trust the other members of the persistent consortium, you just spin up your own node with the federation, and you keep a copy for the content that is important for you. So that's it. It's a very simple way, and there is no incentive other than an external incentive if you want. So for example, if you have an application on the blockchain and you want the proofs to stay available, you should just spin up a node and keep a copy of your own proofs. So this is the idea. And of course, Oraclize could, pay to rent space or whatever once such methods will be available. But at the moment, Oraclize is just basically saying, I promise I will keep a copy of the authenticity proofs. If you don't believe me, just keep a copy yourself via this technique, which is defined in those scripts, and it's very easy to use.
How do you do expansion?
Sorry?
How do you do expansion so you have more possibility of people having it?
Basically, there is just a public, there is the public key of the node, basically, which is encoded in the APFS way. If you go on the documentation of Oraclize, there is the reference to our node. So you can use it to connect to the APFS persistent consortium and become a node keeping a copy of all the files or just some of them. So it's really up to you. Or if you know what are the references of the APFS multi-hashes of the proofs, because for example, you are just monitoring your contract, receiving the callbacks from Oraclize, you don't even need to connect to the consortium, you just go to APFS saying, give me that multi-hash and you keep it. It's just a simple way which is well defined and tells you how to do it, but it's really, I mean, it's naive and it's very limited, but it works well for what was designed. So this is an example. We would like to use it for a couple of things. So the first one is just giving an alternative to people if they want to store the proofs off-chain on Swarm instead of APFS. So the way you do it now, like here, for example, this is a piece of code. This is a piece of code that basically is using the Oraclize APIs, and well, why didn't it compile it? Reasons. Anyway, as you can see here, there is the contract saying I want the proof to use TLS notary as an attestation technique, and I want the proof to be stored on APFS because I cannot verify it on chain anyway. So I prefer to spend less gas and just have the hash on chain. But of course, this could, be Swarm if we were supporting it. So this is one way, which might even replace the persistent consortium, as I said. And the other one I will show you with IPFS, but it's basically the exact same thing with Swarm in that regard. So let's say you have a content on Swarm. If you have the hash, then you can just reference it on chain, but of course you don't want all the content on chain, right? It would be super expensive, and how will you even verify it? It could be very expensive. But if the data you have there is structured somehow, let's say it is a JSON content or something like that, like in this case, you can leverage the Oraclize parsing helpers, like the JSON one, and say, I don't want your content, I just want a specific key. So if you look at this content on APFS, which should be this one. Can
you make it a bit bigger?
Yeah, sure, I will try. Is it, can you read it? No. Okay, so basically, well, this way you will not be able to read anything else. But the idea is that, okay, for some reasons none of the button works.
It's internet.
Ah, it's internet.
Yeah, it's not.
Yeah, whatever. Anyway, the idea is that I did the request before the presentation. So you see that when you ask to Oraclize to get this data from IPFS, it will just return the whole thing, right? But if you specify the parsing helpers, it will say, okay, look, the content is JSON. This is something you know, because I tell you. and I just want a given field. So this is a standard format called JSON path. And Oraclize can send it back, but how do you trust that that content is really coming from there? I mean, Oraclize will claim something different, right? So there are two ways. Basically, one way is to, well, leverage the structure of the content and verify that a given chunk is really part of your thing, but it's not that easy because that, you know, that specific string could be in two chunks, it could be bigger than one chunk. I mean, it's possible, but it was probably not that convenient. Another one, if you want to trust these different trusted execution environments, is just to get a proof from a trusted execution device saying that content is really part of your thing, which is super easy to verify outside the EGAN. Yeah, so this is another idea. I don't know if it makes sense or not, so you tell me. And tools coming from the trusted computing devices can be verified with a reasonable price, which makes it quite appealing. Cool, thank you.